The Compton effect, also called Compton scattering, is the result of a high-energy photon colliding with a target, which releases loosely bound electrons from the outer shell of the atom or molecule. The scattered radiation experiences a wavelength shift that cannot be explained in terms of classical wave theory, thus lending support to Einstein's photon theory. The effect was first demonstrated in 1923 by Arthur Holly Compton, for which he received a 1927 Nobel Prize. The effect is important because it demonstrates that light cannot be explained purely as a wave phenomenon. Compton scattering, the classical theory of an electromagnetic wave scattered by charged particles, cannot explain low-intensity shift in wavelength. Classically, light of sufficient intensity for the electric field to accelerate a charged particle to a relativistic speed will cause radiation pressure recoil and an associated Doppler shift of the scattered light, but the effect would become arbitrarily small at sufficiently low light intensities, regardless of wavelength. Light must behave as if it consists of particles in order to explain the low-intensity Compton scattering. Compton's experiment convinced physicists that light can behave as a stream of particles whose energy is proportional to the frequency. This scattering is more pronounced for shorter wavelengths, such as blue and violet, which explains why the sky appears blue during the day. The longer wavelengths, like red and yellow, are less affected. The scattering of light is not merely a visual spectacle. It plays a crucial role in our understanding of the universe. It helps astronomers study distant stars and galaxies. Scientists have long been intrigued by the nature of light scattering. Their curiosity has led to groundbreaking discoveries. In the late 19th century, classical physics provided a satisfactory explanation for how light, considered a wave, would scatter off particles. This was a significant milestone in the field of optics. However, the dawn of the 20th century brought with it a revolution in physics, the birth of quantum mechanics. This new theory, which challenged the very foundations of classical physics, would forever change our understanding of light and its interactions with matter. Quantum mechanics revealed that light behaves both as a wave and a particle, a duality that has profound implications for science and technology. This dual nature of light continues to inspire and challenge scientists today. Compton effect is the decrease in energy, increase in wavelength of an X-ray or gamma-ray photon when it interacts with matter. Because of the change in photon energy, it is an inelastic scattering process. Inverse Compton scattering also exists, where the photon gains energy, decreasing in wavelength, upon interaction with matter. Compton used a combination of three fundamental formulas representing the various aspects of classical and modern physics, combining them to describe the quantum behavior of light. Light as a particle, as noted in the photoelectric effect. Relativistic dynamics, special theory of relativity, trigonometry, law of coziness. We can think of the photon as losing an amount of energy in the collision that is the same as the kinetic energy, Ke, gained by the electron, although actually separate photons are involved. If the initial photon has the frequency nu associated with it, the scattered photon has the lower frequency nu, where loss in photon energy equals sign gain in electron energy, Hn 1, and the momentum of a massless particle is related to its energy by the formula E equals sign Pc2. Since the energy of a photon is hh nu, its momentum is Ph 3 momentum. Unlike energy is a vector quantity that incorporates direction as well as magnitude, and in the collision momentum must be conserved in each of two mutually perpendicular directions. When more than two bodies participate in a collision, momentum must be conserved in each of three mutually perpendicular directions. The directions we choose here are that of the original photon, and one perpendicular to it in the plane containing the electron and the scattered photon. The initial photon momentum is Hnc, the scattered photon momentum is Hnc, and the initial and final electron momenta are respectively 0 and p. In the original photon direction, initial momentum equals sign, final momentum Hnc rose, Hnc cos up cos 4, and perpendicular to this direction, initial momentum equals sign, final momentum 0 equals sign, Hnc synth 5, from equation 1, 4, 5. We can find a formula that relates the wavelength difference between initial and scattered photons with the angle theta between their directions, both of which are readily measurable quantities. unlike the energy and momentum of the recoil electron. The first step is to multiply x, 4, 5, by CADN. Rewrite them as PC cos fan, HNA cos, 6, PC synth alstant synth, 7. By squaring each of these equations and adding the new ones together, the angle pH is eliminated, leaving P2C2 equal sign HN 22 HN 100 cos chen 2 8. Next we equate the two expressions for the total energy of a particle E equals sign Ke plus Mach 2 9 E clutch M2C plus P2C2 U 10. From equation 1 we have P2C2 equals sign HN22 HN to Chen 2 plus 2 MC2 NHN 11. Substituting this value of P2C2 in EQ 8, we finally obtain 2 MC2 HN10 equals sign 2 HN N 1 cos 12. This relationship is simpler when expressed in terms of wavelength lambda, dividing EQ 12 by 2 H2C2 EMSC HNC NC NCs NC 1 cos 13, and so, since NC 1L and nu C1L MCH 1L 1L equals sign 1 cos L14 LL Mach 1 cos 15. Equation 15 gives the change in wavelength expected for a photon that is scattered through the angle theta by a particle mass m. This change is independent of the wavelength lambda of incident photon. The quantity LC8HMC 16 is called the Compton wavelength of the scattering particle. For an electron LC2 of 46 at 12 mem, in terms of LC-EQ, 15 becomes LLLC 1 cos 17. The Compton wavelength gives the scale of the wavelength change of the incident photon. From EQ 17, we note that the greatest wavelength change possible corresponds to the 180, when the wavelength change will be twice the Compton wavelength LC. Because LC can 00243 nm for an electron, and even less for other particles owing to their larger rest masses, the maximum wavelength change in the Compton effect is 0.004852 nanometers. If the photon is of lower energy, but still has sufficient energy, in general a few eV, right around the energy of visible light, it can eject an electron from its host atom entirely, a process known as the photoelectric effect, instead of undergoing Compton scattering. Higher energy photons, (MeV), may be able to bombard the nucleus and cause an electron and a positron to be formed, a process called pair production. Imagine a beam of X-rays, like tiny invisible bullets, hurtling towards a target material, such as a thin sheet of graphite. Within this material lie countless electrons, much lighter than the X-ray photons but still possessing mass and charge. Compton's experiment was elegantly simple. He directed a beam of X-rays at a target, and then used a detector to measure the wavelength of the scattered X-rays at various angles. What he found was astounding. The scattered X-rays had a longer wavelength than the incident X-rays, and the amount of wavelength shift depended on the angle of scattering. This was a clear violation of classical physics, which predicted no change in wavelength. Compton's experiment provided compelling evidence for the particle nature of light and revolutionized our understanding of light-matter interactions. Section 5. Conservation laws. The universe plays by the rules. To truly grasp the essence of Compton scattering, we need to delve into the fundamental principles governing this intriguing phenomenon: the conservation of energy and the conservation of momentum. These laws, like cosmic accountants, meticulously track the energy and momentum of particles involved in any interaction, ensuring that nothing is lost or gained out of thin air. Imagine the X-ray photon as a tiny billiard ball colliding with a stationary electron. Just like in a game of pool, where the total energy and momentum of the balls remain constant, the same holds true for the photon-electron interaction. The photon, upon colliding with the electron, transfers some of its energy and momentum to the electron, causing it to recoil. As the photon loses energy, its wavelength increases, explaining the observed wavelength shift. Section 6. Unraveling the Compton Formula, a step-by-step journey. Now let's translate the principles of conservation of energy and momentum into a mathematical language that describes Compton scattering, the Compton Formula. This formula, A testament to the power of physics to quantify the universe, allows us to calculate the change in wavelength of the scattered photon based on the scattering angle. The Compton formula can be expressed as dl equals sine h MOC 1 cos, where dl represents the change in wavelength, ah is Planck's constant, m rho is the electron's rest mass, c is the speed of light, and theta is the scattering angle. This formula encapsulates the essence of Compton scattering, highlighting the inverse relationship between the change in wavelength and the cosine of the scattering angle. Section 7. Applications of Compton scattering, from X-rays to astronomy. Compton scattering, far from being a mere theoretical curiosity, finds widespread applications in various fields, ranging from medical imaging to astrophysics. In medicine, X-ray imaging relies on the scattering of X-rays by bones and tissues to create images of our internal structures, aiding in the diagnosis of fractures, tumors, and other ailments. In astrophysics, Compton scattering plays a crucial role in our understanding of high-energy phenomena, such as gamma-ray bursts, the most powerful explosions in the universe. By studying the scattered gamma rays from these events, astronomers can glean insights into the extreme physical conditions that drive these cosmic cataclysms. Section 8. The enduring legacy of Compton scattering. Compton scattering, a cornerstone of modern physics, stands as a testament to the power of scientific inquiry and the importance of questioning established paradigms. Arthur Compton's groundbreaking discovery not only revolutionized our understanding of light-matter interactions, but also paved the way for the development of quantum electrodynamics, a theory that describes the interactions between light and matter with remarkable precision. The legacy of Compton scattering extends far beyond the realm of physics. It serves as a reminder that our universe is full of surprises, and the pursuit of knowledge is an endless journey. Compton scattering is of prime importance to radiobiology, as it happens to be the most probable interaction of high-energy X-rays with atomic nuclei in living beings, and is applied in radiation therapy. In material physics, Compton scattering can be used to probe the wave function of the electrons in matter in the momentum representation. Compton scattering is an important effect in gamma spectroscopy, which gives rise to the Compton edge, as it is possible for the gamma rays to scatter out of the detectors used. Compton suppression is used to detect stray scatter gamma rays to counteract this effect.